Hi, I'm Koso Tavzo, secondary one for NS High School. In this lesson of ordinary differential equations right now here, what we're going to have will be, you can call it sort of a revise. You can also call it a preparation for the next lesson, as what we'll be having in this lesson will be needed for the next lesson. And the next lesson will be very weird, a new method to solve them. But you're using sine and cosines. You're playing around with them, okay? So for this part that I'm going to have first, so it's just sort of a revision so that you need to use them in the next lesson. So for the first part that you definitely have to know. Okay, you know dy, right? So dy, you're just saying it is dy dx. But wait, what if I change it a bit? I change it into y over d. Or if, other than using y, you can also use fx just to represent that function of x. What if I use y over d? Is it equal to, since d is d over dx, is it dx y over d? Well, let me just tell you, you can't reciprocal like that, and so this part is wrong. So for this part, what is it actually? Okay, let me just tell you. Y over d, d for this part, you're representing it as an operator. So this part that you're going to use will be integrate y dx. So this part is just an integration that you will have. So this is one of the parts that I'm just going to remind you of. So when it seems like d times, it is a differentiation. When it seems like you divided by d, it is integration. Oh wait, over d, does this remind you of something? Does this remind you of something that we have done some time ago? Or we are just keep using it for the past lessons? You have a function, then you over d plus something. It may be m, it may be n. There are different things to it. We had something like this. And then you're saying that it is equal to e to the power of negative mx. Then you integrate fx e to the power of mx dx, right? Oh wait, can we prove this over here? So in this part, we need to prove this thing. So to show this, first of all, wait, we had a y being equal to that, right? Yes, we can't miss out that y, right? So this y gives us actually a clue. So what if we sort of move this on the side, like we reverse that process a bit. I guess we reverse it until here. Then from this part here, you put it back again. So first part, okay, d plus m. D for this part, you differentiate y. So you get dy, or you can write it as y prime. Then plus my. Is it saying the English word my? This is m. Well, m here, constant. Then you times a y. Then you have it equal to fx. Let's recall what we have learned, well, at nearly the beginning of our ordinary differential equations. It is one of the first few methods that we had. Okay, if you recall it, here you have y prime, then here you have plus. Okay, if you just change this form, this y prime gives you a little bit more clue about what you have. Okay, let me just tell you, we're going to use the integrating factors method, okay? So integrating factors, the part that we are going to use, e to the power of, okay, so you integrate. But from this part, beware, you're using p. as in what we had originally for our integrating factors. We're using a p for this part, like px, y. So px now is an m. So you have m, then dx. So what you're going to get will be e to the power of, since m is a constant, so m doesn't change, and it directly times x. So it is e to the power of mx. The integrating factor, we times it on both sides. Right. This is the part where we had our integrating factor. Then from this part, let's just take it as we use e to the power of mx. Well, that means here we actually use total differentiation. So we have to recall a lot of methods here. So we use total differentiation. Then if we try again, y, you differentiate, yes, y prime. Whereas e to the power of mx doesn't change. And same for the other part. Okay. Then after that, here you have d. What if you integrate this part? So from here, wait a second. So you have this y prime here, right? So from this y prime here, it is dy over dx. And when you want to use this total differentiation, it is you're using dy, and then you have a dx, then dx. So here you get a dx on the other side. Okay? Then you both sides integrate. Like this. So then after that, one more step to find y. You just need to divide this to the other side. But when you're dividing this e to the other side, that means you're just changing a negative sign on the power. So you get y being equal to e to the power of negative mx. Then you integrate fx. Then e to the power of mx dx. Now this is still familiar. You compare it with the one above. Yes, we have got it. So actually, we have already proven it. Alright. So we have already proven this part, and this is the second thing that I'm saying about. Just to show you, right before we start the next video, you already know this is true, in case you doubt that this is not true at all. So here I've proven that it is true. Then the next part, if you already have a function like this, or because that a function like this, after you solve it, it will still be a function. So you can just take it as an fx. Since no matter after how many times you solve, well, you still get a function of x. And for that function of x, you can call it fx. Okay. Then what if we had d plus m on the numerator and then d plus m on the denominator? Would this change still cause it to be equal to fx? Would this be alright? Would this change be possible? Some of you may just say, well, you just simplify them. Simple as that. But wait, be careful. Here you're dealing with operators. And when you're dealing with operators, beware. Operators, d, for this part, it is d over dx. You cannot just simplify them randomly. You cannot just say, okay, let me just cancel them out. Then after I just times d, divide by d, times and divide. So you have to be aware. You can't just simplify them just like that. Okay, so there's one part that it is. So let's just take it as we differentiate it first, okay? So if we differentiate it first, then we'll have 1 over d plus m. So when you differentiated it, you get f prime x. So this is if you differentiate it first, okay? So f prime x. Then for wait, how about that m over there? That m over there, it means you have the plus m f x. Okay, so this is part that you have. Alright, then you have to integrate. Then for this integration part that you're going to have, you will integrate. So f prime. Now f prime, what would you have? But you also have to be aware that you have an e to the power of negative mx out here, as we have just proven this, right? And then inside here you have e to the power of mx dx. Then for the second part, so first part you have this, second part you have, okay, m just as a constant, you can just take it out. So inside here you will be left with fx. So inside here e to the power of mx, then dx. So this is the part that you'll get after your integration. Oh wait, can we just conclude straight away that this is equal to fx or it is not equal to fx? We still can't conclude straight away. Alright, so let's simplify some more. So from this part, what if we continue to simplify? Let's see. If we put e to the power of mx inside, oh wait, after they change using integral by parts, you get f prime prime. So you cannot use that. So what if I put f prime inside? So that means you get fx there. So let's just give it a try. Like this. For the back part, we just keep it the same first. Then afterwards, for this part, we can use integral by parts. Integral by parts, then you have a negative e to the power of negative mx, then integrate fx d e to the power of mx. And then afterwards, you want to say, you take this out of the d. But wait, this part, then you suddenly realize, you could just directly write this as fx. Then subtract. So differentiate m e to the power negative mx, then integrate. Okay, so it's this whole bunch left. Okay, like this. Then you compare these two parts. They're all the same, except this is negative, this is positive. So, what you could get will be fx. So this is the part that I got. Well, in this case, you're differentiating first, then you're integrating. Then, some of you may say, well, what if I integrate first, then I differentiate? Would it be of a change? Okay, if you want to have that, then I'll try here. So integrate first, then you differentiate. So that means you're left with d plus m. So when you're integrating, you have integrate. Oh wait, beware of that d plus m. So that means you'll still get e to the power of negative mx. And also you cannot leave out this x here. Fx, then e to the power of mx, then dx. Alright. So you have to differentiate this part. How can we differentiate? What if we try to use product rule? So if we use product rule, differentiate this part first, you get negative m e to the power of negative mx. Then the back part is same. Therefore, this part behind, you differentiate it. And what happens next? So you get plus e to the power of negative mx. Yeah, wait, you differentiated this. So this part is what you've gotten. Alright. So is there other part here? So you're using for these two. And there's also another part, if you didn't miss it out. So the part that I have done is only for D. The other part left will be for M. So in case you're wondering why was that wrong, this was the reason. Okay, so one more last part. You have to add M e to the power negative mx. Then you integrate fx e to the power of mx dx. Then you compare these two parts. Okay, they're actually the same, just that this is negative, this is positive. So these two will cancel out. Then the only part left here. So e to the power negative mx and e to the power of mx, they'll cancel out. And what you will be left with will be fx. So that means in total, d plus m fx over d plus m, it is equal to fx. So this part is proven. That means in the next video, when we need to use this, yes, we could use it already. But wait, you could times and you could divide and you could use them interchangeably, or like at different positions, whether you differentiate first or whether you integrate first. So this is like a commutative law, okay? So that's actually what you're having, or what, at least you're assuming that you could use, as it appears to be like that. So let me just tell you again the parts that we have shown. So just remind us, this part is what we had, this part and this part. So these are just some of those that we will need to use in the last lesson here. I mean in the next lesson, alright? So from here, just to tell you, here I've used one method to prove this, then here I've used two methods to prove it, alright? So I'm just going to end this lesson here. And if you like our videos, don't forget to subscribe to our channel. We'll see you in the next lesson. Thank you for your watching.